Just before our internals in the last class, we were discussing about the frequency response of a common source amplifier. And we said, in general, we need all amplifiers to exhibit what? The ideal frequency response of all amplifiers would be a straight line like this. That means with change in frequency, we don't want the gain to vary. That is the ideal response expected in all amplifiers. But we know that practically it is impossible to have a constant steady gain as per design at all the frequencies. So the graph of the gain in decibels, okay, V naught by V sig, the overall gain GV in decibels to the frequency in hertz plotted on a logarithmic scale is known as frequency response. So what is frequency response? It is the plot or graph of the gain in decibels along the y-axis versus frequency in hertz along the x-axis. But this frequency is plotted on a logarithmic scale. It's not plotted on a regular scale. This gain is plotted on a regular scale, but the unit of gain is decibels. I told you bell was the unit coined because they decided the best thing is it should match with our audio range, human hearing range or human audio range of our ears. So our ears could tolerate volumes or power levels in bell would have been too high, decibel would be something better. So they decided to use 1/10 of a bell or decibel as the unit for gains. Because the initial amplifiers which were designed were mainly as audio amplifiers. Only then they started to be used for other various purposes for video and other things. But the first set of amplifiers were basically designed as audio amplifiers so that they can magnify the sound and send it over a long distance through the telephone wires and so on. Hence, the unit of gain was decided as decibels, and gain is plotted along the y-axis, frequency along x-axis. And why we take a logarithmic scale for frequency? I told you this. That is mainly because we get a large range of frequencies. If you take a normal scale, if I have to plot from 10 hertz to 1 megahertz, you'll need a very long graph sheet. Imagine if you use or you'll miss the finer points. See, as you notice in the practical frequency response, there is variation only in the lower frequency range and in the higher frequency range. In the mid band or the middle frequency range, the gain is almost constant. So I need to plot, I'll have different points in this 10 hertz, 20 hertz, 50 hertz, 100, 200, so on. And I'll have points to plot in the megahertz range also. Say 500K, 1 mega, 2 mega, 3 mega, so on. That means I can't accommodate everything on a such huge variation on a normal scale. And if you want to accommodate, you will need a very lengthy graph sheet, a very long one. So they came up with the idea of using a log scale for the frequency axis, where we get a complete picture in a smaller single graph sheet. So when I use logarithm of the frequency values, we know log 10 is 1, log 100 is what? 2, right?
2.
Accordingly, log 1000 is 3, so on. So you would get the plot on a small scale and the complete variation can be captured effectively. Usually in amplifiers, what we notice that the gain remains as per design only at the middle frequency band, and that is called the mid band. This region is called the mid band, where the gain remains almost constant as per design. And from where to where are we going to consider that mid-band? If you remember in the last class, I told you all this. We consider the mid-band region till starting from the point where the maximum power, maximum output power is half its value till it reaches the max power, and again it reduces to half its value. So we said all amplifiers could be used even if the power level came down to half the value, they could still be functioning fine. Whatever the design purpose, it could be served even if the power level came down to half its value. But below that, the amplifiers could not be used. Their parameters would change. Hence, that useful range of frequency where an amplifier can be used ranges from half power to full power, and the first half power point is called the lower cutoff frequency FL. The second half power point is called the higher cutoff frequency FH. Okay, and the difference between FH and FL is known as the bandwidth of the amplifier, which represents the useful range of frequencies for a given amplifier. Okay, that's the range in which an amplifier can be used as per design. It can be working as per design and you can use it efficiently. But if I go below FL, you will see a drastic reduction in the gain. Do you remember what is the reason for this? It's here mentioned. The gain falls off at low frequencies because of coupling and bypass capacitors. Remember, these are the coupling capacitors and this is the source resistance bypass capacitor. So these are the capacitances which cause a reduction in gain at low frequencies. And again, when we come to the high frequency range also, we'll see a drastic reduction in gain. And what is the reason for this? The reason for this is the what? Device capacitances. The device capacitances in the MOSFET, like that CGS and CGD. You remember we wrote the high frequency model where we said two major device capacitances come into picture. One is the CGS, gate to source. The other is the CGD. Hence, these are the capacitances which affect the drastic reduction in gain at high frequencies. Okay. Hence, the frequency response of a common source amplifier will look something like this. It will increase from low to high in the low frequency range, and in the mid frequency it remains almost the same constant. High frequency again it decreases. And let us try to see and derive why this happens. So we'll start off with the high frequency response of the common source amplifier. Let's consider a common source amplifier as shown, where we have the input signal generator Vsig given here with its internal resistance Rsig, and CC1 represents the input coupling capacitance, Rg is the biasing resistor, and this is our MOSFET. Here we have used constant current biasing, which you haven't studied actually, but that's the one which is considered here, where a constant current source will be present in the source region, which will be connected to the negative of a DC power supply minus VSS. And we know that any element in the source causes negative feedback, just like the source resistance. So there will be a source resistance here to have a constant current source. I'll have a complete circuit, amplifiers, MOSFET current source circuit here. So I have to bypass it with a bypass capacitance. You can see here this CS is a large capacitance which is normally called as the bypass capacitance. Okay, that is CS. CC1 and CC2 connected on the input and output side are the coupling capacitors. These are the coupling capacitors. RD as usual here is the drain resistance across which we are going to measure the output. And we have the power supply, DC power supply VDD given here. Okay. And we also have a load resistance RL connected in this circuit. So our objective here is to identify the mechanism which limits the high frequency performance of these important amplifier configurations like the common source amplifier which we have considered. Also, we need to find a simple approach to estimate the frequency at which the gain falls below 3 dB and from its mid-band range. Okay. So first, our approach will be to find the mid-band gain, and then we will find at this point the gain comes. I'll have to find AM, the mid-band gain first, and then I'll have to find the gain at which this point occurs, where it is 3 dB less than the mid-band gain. I'll call that as the high frequency gain AH. Okay. So our objective in our analysis now, first determine the mid-band gain, then determine 3 dB below the mid-band gain, whatever is the gain, that is the gain at high frequencies. And when this happens, what is the corresponding frequency, which is known as the higher cutoff or upper cutoff frequency of an amplifier. So we have to find all these things in this analysis. Okay, is that clear? So first thing, let me find the gain at mid frequencies first. Gain at mid frequencies should be found. Now, can you tell me what would be the equivalent of this amplifier at middle frequencies? Remember, in the middle frequency range, we assume all these capacitors as short circuits, and the device capacitances of the MOSFET would not have been activated. They would not come into picture. Okay, so please remember this. You can just write at mid frequencies, all capacitors are considered as short circuits and device capacitances do not come into picture. They are so small that they need not be considered. Therefore, to obtain AC equivalent circuit, short all the DC sources and capacitors. Short all DC sources and capacitors. So let's do that. Let me redraw the AC equivalent circuit. How does it look? AC equivalent circuit for the common source amplifier. Remember, I have a current source here, and this current source which is connected to minus VSS. Minus VSS means this is the connection. This is how I am going to connect the supply. But across this, I have a capacitance here. So what do you think will remain in the AC equivalent of this part? What will happen to this capacitance?
Short circuit.
It should be replaced with a short circuit. So if I have a short circuit across these elements will not have any effect on the behavior of the circuit. So it is in effect, the source will be shorted to the ground. That is the lower part of the circuit. Next, coming to the drain. From the drain, I know I have a resistance RD. That resistance is connected. One end of that resistance is connected to VDD. But remember, this VDD is a supply like this, positive. This is VDD, and DC power supplies should be shorted for AC operation. So this RD, the drain resistance, will be connected between the drain terminal and ground, like what I have written here. Okay. So drain terminal and ground, it will be connected. Then what else do I have on this side? I have this coupling capacitance CC2 that should be effectively replaced with a short circuit. So again, I will have RL included in parallel with RD. So in the AC equivalent circuit, you have RD in parallel with RL between the drain and the ground, and the source will be grounded. The output voltage is measured here from drain to ground. And let's reproduce what we have on the input side correctly. On the input side, I have a resistance between gate and ground. This coupling capacitance acts like a short. So I'll just have to directly connect Vsig and Rsig. So here, we have Rg, the biasing gate resistance, and then I have Rsig and the voltage source Vsig. This would give us the AC equivalent circuit. So you need not write this actually. I just wrote it to show that a bypass capacitance effectively removes anything else which is connected in the source. So any other element that is connected in the source will not have any effect. Okay. So once you have the AC equivalent circuit, what is the next step? The next step is to replace the MOSFET with its small signal model. Replace MOSFET with small signal model. And here small signal low frequency model only we are going to consider, because we are trying to analyze the behavior at mid frequencies. Low and mid frequencies, it's the same model which we discussed in module 1. So you see what is shown in this darkened diagram. This will be the replacement for the MOSFET. The MOSFET is replaced with this. What do I have? I don't have anything connected between the gate and source. It indicates open circuit or very high input resistance, infinite input resistance, represented as an open circuit, where the gate source voltage VGS is applied, and between drain and source for the MOSFET, I have a dependent current source GM into VGS. The value of the current flowing between drain and source will be GM into VGS in parallel with the output resistance R0 of the circuit. So this would be the replacement for the MOSFET in low and mid frequencies. I'm using this to find the mid-band gain first. So let's find the mid-band gain. Therefore, the mid-band gain AM is defined as V0 by Vsig when RL is present in the circuit. If you want, you can say with RL not equal to infinity. So for this complete circuit, we just have to find the ratio of output voltage to the actual input voltage. Where do I measure the output voltage? The output voltage is measured here. See, all what I have done is I've replaced this MOSFET with its small signal model. The remaining elements I have written as it is. On the input side, you have Vsig, Rsig and Rg, same as what is there in the AC equivalent circuit, connected between gate and source. And on the output side, we have Rd in parallel with RL, connected between drain and ground. Hence, we have just replaced the MOSFET here with its small signal model. That's all. We have done this often. Common source amplifier, we analyze two types, common drain, all that. Now our job is to just find the voltage gain of this circuit. Let's define what would be the value of V0 here. Can you tell me the equation for V0? You have one current flowing through a parallel combination of three resistors, right? I can call this resistance as, say, RL dash, which would be small r naught in parallel with capital RD in parallel with RL. So all these three resistors could be replaced with a single resistor RL dash, and the current flows through this resistor, creating a voltage drop in this direction, lower end negative, upper end positive. But we are measuring V naught in the opposite direction. So what would be the value of V naught? Minus of the given current source GM VGS into RL dash, which is R naught in parallel with RD in parallel with RL. So this would be the value of the what? Output voltage. And if I have to ideally consider this voltage V6, this would be, what would happen? Can we write V6 in terms of VGS if we want to write? We will have VGS is equal to V sig RG by R sig plus RG. Remember, the voltage divider rule can be applied if I want to find the value of VI or VGS. VI and VGS are the same. VI, VGS are one and the same. It is the voltage drop across this resistance RG. But what we can do is we can assume for now that this voltage, output voltage will be this, or let me directly write the midband gain. Midband gain can be written as minus GM VGS into R naught parallel RD parallel RL into, divided by, I want, instead of V sig, here we have V sig. What do I want? I want the voltage in terms of VGS so that VGS cancels and I'll be able to write the value of midband gain. So what is V sig in terms of VGS? It will be VGS into R sig plus RG divided by RG. Yes or no? So this will be VGS into R sig plus RG divided by RG. Then VGS cancels out, or I will have the midband gain effectively as RG by R sig plus RG. You remember, this is the standard solution. Whenever there is a biasing resistance, the voltage which appears at the input side of the amplifier will not be same as the signal generator voltage that is supplied. So it gets divided between the signal generator internal resistance and the biasing resistance, which is given by this ratio, right? Into GM, again minus, into this R naught parallel RD parallel RL. This is our actual midband gain. Let's call this equation 1. And V naught is actually given as minus GM VGS into RL dash, which is R naught parallel RD parallel RL. Okay, we can call this as RL dash. Remember these two equations. Now, let's move on to find the high frequency gain. So the next step is to find high frequency 3 dB gain of the CS amplifier. I hope there is no doubt in finding the mid-frequency gain. In mid-frequency, the amplifier MOSFET will be replaced with its simple model which we have considered. There are no additional capacitors or anything. But once we go for high frequency analysis, the replacement for MOSFET should change. Here you say device capacitances device capacitances are active. Therefore, the small signal equivalent model for the MOSFET should be the high frequency hybrid pi model. The high frequency model which we have written, that should be used to replace the MOSFET. So do you remember what is that hybrid pi model which we had considered? It involved one capacitance here between the gate and the source CGS, and one more capacitance between gate and drain CGD, and this is the drain terminal, and at the drain terminal we have, as usual, the dependent current source GMVGS, right, in parallel with the output resistance R0. So if I have to write the high frequency model, even before grounding this, one second. Yeah, this is the high frequency model for the MOSFET. So between gate and source, usually we would never have anything in the low frequency model because the resistance was infinity. In this model, we don't have anything. The resistance is infinity. But at high frequencies, there is a capacitance coming into picture. So CGS is that gate to source capacitance which is active. Now, between the gate and drain, there is another capacitance coming into picture, CGD. This is our simplified high frequency model. Remember, here we have assumed that source and substrate are shorted. You see in this circuit which we have written, we have shown only the source terminal. So here you have to assume what? Source and substrate are shorted, and that's why we are not considering the second current source which was GMB into VSB, the source to body voltage. That is not there now because it is 0. So the second current source and the two capacitors have been neglected. The drain to body and source to body capacitance have been neglected. Among the device capacitances, we have gate to source, gate to drain, then drain to body, source to body capacitance. Both of them have been neglected. Source to body capacitance will be 0 when the source and substrate are shorted. Drain to body capacitance will be very small, hence it is neglected. So please remember, this is your high frequency equivalent model of the MOSFET. Okay. So now this is the replacement for the MOSFET. This is the high frequency model of the MOSFET. Now you bring the other elements from this AC equivalent circuit. I've just replaced the model MOSFET with a different model. That's all. Remaining elements, you just bring it as before. What should I write on the inputs? First thing, the source should be grounded. On the input side, I have to consider the biasing resistance, the signal generator resistance R sig, and the signal generator V sig. Okay. So this is what you have to consider on the input side. That's all was there in this AC equivalent circuit. V sig, R sig, RG between the gate and source, or between the gate and ground. On the output side, we have RD in parallel with RL. So those things let me include RD in parallel with RL, and we'll measure the output voltage here. Okay. Hence, this represents our small signal equivalent circuit at high frequencies. Do you have any doubts with this? Remember, we already derived this high frequency model and we have analyzed. Only when we are operating this MOSFET device at high frequencies, I'll be making use of this high frequency model. Is that clear? So we have replaced the MOSFET with its high frequency simplified model. Now we'll simplify this one more step. Let me write the equivalent for this one more step. I can consider if I look between this terminal and this terminal, what will be the Thevenin's equivalent of these two resistors? See, if you are looking between the gate and source towards the input side, what would be the Thevenin's equivalent resistance seen here? Whenever you are using Thevenin's theorem, you will consider this source as a short circuit. Any voltage source will be acting like a short circuit, current source as open circuit. So what would be the equivalent resistance?
R sig parallel to RG.
R sig parallel RG. So what we'll do, we'll replace the two resistors to simplify the model with R sig dash, which is nothing but R sig in parallel with RG. Instead of writing these two, instead of using multiple loops to analyze, we have to simplify this circuit as far as possible. So I'll just replace these two resistors with its Thevenin's equivalent and in series with V sig as shown on the input side. So here I have to account only for this gate to source capacitance CGS, okay, and the voltage across this would be VGS, the gate to source voltage, and from here onwards I have the capacitance between gate and drain CGD. Let's consider the current going through this as IGD, the current going from gate to drain as IGD through this capacitance. It's the same thing. Here I have the current source GM VGS, and what can I simplify all these three resistors put together as? It is nothing but RL dash, which is R0 in parallel with RD in parallel with RL. We had considered that in our previous circuit also. So all the three put together, I'll consider it as RL dash. Okay. And the output voltage which we have to measure is across this RL dash. So what did we do? We got the simplified high frequency equivalent of the common source amplifier. Okay. And this part is grounded. Any doubts so far? So once you have this, let's try to analyze this circuit and obtain, we have to find what is the voltage gain of this circuit. So during high frequency operation, the MOSFET equivalent circuit will be something different. Yes? Any doubts? Okay, during the high frequency operation, the MOSFET equivalent circuit will not be same as what it was during low frequency operation. So we have replaced it with a different model, and let's try to find the voltage gain of this circuit. So in order to find the voltage gain, first let me try to find the value of IGD. Let me find the value of this gate to drain current. So if I write an expression for this gate to drain current in terms of this capacitance, then I can replace this capacitance by writing it from gate to ground, and I can remove this connection. Then the whole circuit would be simplified. The main problem here is the input and output side are connected with this capacitance. If we are able to separate the input and output side, our analysis becomes very simple. So what is the expression that can be written for this current IGD? The current IGD can be written as, what do we write usually? The voltage, what is the expression? See, what is the reactance of a capacitance? XCGD is 1 by SCGD. We can write it like this. S is nothing but J omega. We know in terms of S parameters, if I write, the capacitive reactance XCGD can be written as 1 by SCGD, and S is J omega. We know that. And if I want to find the value of current through a capacitance, what would it be? It would be the voltage across that capacitance divided by the reactance of the capacitance. Yes or no? So what would be the voltage across this capacitance CGD? What is the voltage at this point? What is the voltage here? Isn't it VGS? The voltage here at this end is VGS. And what is the voltage at this end? It is V0, the output voltage. If it is V0 here, it is V0 here also, V0. So you can see that the voltage at the gate is VGS. The voltage at this end is V0. So what would be this voltage? Let me write it here only. By XCGD. VGD is this clear now? See, the current through this capacitance can be written as voltage across this capacitance divided by its impedance or reactance. And the reactance of a capacitance can be written as 1 by S CGD, because we are calling this capacitance as CGD. So 1 by SC is the reactance, capacitive reactance. What is the voltage drop across this capacitance? VGS on this gate side and V0 on the drain side. Output voltage appears here. The gate source voltage appears here. Therefore, I can write the voltage drop across this capacitance should be the voltage at this end minus voltage at CGD. It is, or VGD is nothing but what? VGD is VG minus VD. So what is the voltage at gate? VGS. And what is the voltage at drain? V0. Hence, the voltage difference between this is VGS minus V0. That divided by the capacitive reactance, which can be written as 1 by SCGD, or I can write an expression for the current through this capacitance IGD will be SCGD into VGS minus V0. Next, what I'll do, I'll say we know that since the output voltage is nothing but the voltage between drain to source, the gain from input to output is given as GM into RL dash, or let me say minus GM into RL dash, which is same as the midband gain. I'm just writing what was the midband gain in this circuit. See, if I try to find the gain from this point, see, if I just want to find the gain from this point till the output, if I want to find the ratio of V0 by VGS, V0 will be minus GM VGS into RL dash, divided by VGS. So what will I get the gain from here to the input side is VGS and the output is V0. So you will clearly get the voltage drop here across this is minus GM VGS into RL dash. We have written n times already. That divided by VGS will give me the gain from output to the input side. I haven't considered the complete gain. I just want to consider what is the gain here, and we have obtained this value. This is nothing but minus GM into RL dash, which is almost same as the mid-band gain. Okay. Why I am telling almost? Because we haven't accounted for Vsig being different from VGS. If Vsig and VGS are almost the same, then which is same as mid-band gain, when VGS is approximately equal to Vsig, or you can say Rsig is very, very small. When you can write it like this also, Rsig is much, much less than Rg. So either of these conditions, I can use this relation, and I'll say the gain can be given as minus Gm into RL dash. So what do I want to write? Therefore, V0 can be written as the gain into the input voltage. Which input voltage have we taken? VGS. And what is the gain value? GM RL dash into VGS. Therefore, the output voltage V0 can be written as the gain of the circuit into its input voltage. Since I am considering only this voltage, not the complete Vsig, I'll just say VGS into gain, and that gain is given as minus GM into RL dash. Now, let me substitute this value in equation 3. In equation 3, I have a V0. For that V0, I am going to substitute this value. You say, using equation 4 in equation 3, what is the expression you get for this current? We have SCGD into VGS minus V0 I had. For V0, I am going to replace it with minus GM RL dash VGS, right? This is the expression. Let me simplify this. I think VGS also can be taken as the common factor. What is left here? 1 minus into minus plus GM RL dash. So I can write this gate to drain current IGD as the capacitive reactance or 1 by capacitive reactance SCGD into 1 plus GM RL dash into VGS. Let me call this expression as equation 5. Now, can I rewrite this, let's say, rewriting the equivalent circuit as follows. We have the small signal equivalent circuit here. So what I'll do, I'll try to separate the circuit and I'll shift this capacitance between the gate and ground, and I can do that if I know the value of this current IGD. See, when can I do the disconnection from output to input side? If I'm able to determine the exact value of this current IGD, I'll just disconnect this capacitance CGD from the output side and rewrite it across the input in parallel with the input. So let's try to do that. What would it look? So let me say, I'll write it something like this. We have Vsig Here I have R sig dash, okay, which is Rg in parallel with R sig. Here I have the capacitance CGS. That part is same as what we have here. CGS we have, and this CGD, I'll replace it like this. But the current through this is IGD. The voltage here is VGS. Okay. The current here is different. And on the output side, I have this GM VGS as before. No changes there. Across RL dash. Across this, we were trying to measure our output voltage V0. So the drain terminal and gate terminal have been separated by bringing this capacitance in parallel with the, I can't write it as IGD and CGD. If you want, you can write. Later on, we'll replace this combination. When I want to put it here, it won't be, I can't have the current and voltage like this. I'll call this, I have to call this as a new capacitance C equivalent. I'll write it like that here. The value of the capacitance will change. Why, can you tell me? What happens to this? Can I write it? Let's say this SCGD into 1 plus GMRL dash. Can I call it as S into C equivalent? See what I'm trying to do. This whole thing is replaced with a new capacitance C equivalent. This S I am considering as it is, VGS is there. You say where C equivalent is nothing but the old CGD which we had connected between the gate and drain into 1 plus GMRL dash, where GMRL dash represents the mid-band gain of the amplifier. You call this equation 6. So IGD can be effectively written as SC equivalent into VGS. What is the purpose of writing like this? You see, if I replace this capacitance CGD which was connected from gate to drain with an equivalent capacitance C equivalent which is connected between the gate and source, you see the voltage across the capacitor is now VGS. Don't I have that voltage here? Since the value of this current is voltage divided by reactance, the voltage which I have now is VGS. That's why it justifies my replacement of the capacitance in parallel with this gate source voltage or in parallel with the gate to source capacitance CGS. So the voltage across this capacitance C equivalent is still VGS as in the equation and as in this equivalent circuit, and the current through this capacitance remains as IGD, which is SC equivalent into VGS, and the value of this equivalent capacitance would be CGD into 1 plus GMRL dash. Please remember this, and that will give us the basis for simplification of this circuit. Any doubts with this? So the circuit can now be replaced with this capacitance. Now can we find the expression? What would be the expression for the gain? Let me simplify one more step before that. I have V sig, I have R sig dash, and these two capacitances in parallel, I'll replace it with a single capacitance What's the value of these two capacitance when I have two capacitances in parallel? What can I write it as? I'll call it as a single capacitance. We know capacitances in parallel will add up. Yes or no? Just like how resistances in series add, capacitors in parallel will be direct addition. So the new input capacitance can be treated as the parallel combination of CGS and C equivalent. And remember, C equivalent is CGD into 1 plus GM RL dash. And C in is these two combined together, which will yield one single capacitance. As usual, on the output side, we have the dependent current source in parallel with the combined load resistance RL dash. So now we have the simplest form of this circuit. So whatever circuit we started off with for the high frequency model, we have it in its simplest form now. And if you look at this circuit, this is called what type of filter? Do you remember studying this? An RC circuit like this. What do we call this as? This is called as a what? Low pass filter. What is a filter? A filter is a circuit which retains certain, say the input signal is represented like this. This is V in. A low pass filter is something which will retain the input signal at low frequencies but attenuate the input signal at high frequencies. This is the response, practical response of a low pass filter. Ideal response will be a straight line like this. Suddenly it should limit, but practically that won't happen. This is the response of a low pass filter. This can be V0 or V0 by Vi, and this is frequency. So what is a low pass filter? A low pass filter is a circuit which passes the input signal with gain as 1. So here V0 by Vin will be 1. It will have the gain as 1 at low frequencies. We can also have a higher gain if I include an amplifier here. Later on I can show inclusion of an amplifier here. You'll be doing it in the lab. In the next class, just understand a low pass filter has ideal response like this. Its job is to pass the given input signal as it is at low frequencies and attenuate the signal at high frequencies. This is ideal and this is practical.